Last time we were discussing idea was suppose your channel is X and Y. You want to go from here to a company X and Y. Where understood. And that's our repetition of now. The question is, what do we do with this? With something useful, we can make up with this. Any questions from last time? No. Okay, so let's just something on it. Let's say we're going to look at physical distributions. So this is a theorem that indicated last time. Today we are going to conclude that's for any two discrete distributions there exists x hat y hat of x comma y like that. Probability that x hat is not equal to y hat is equal to 1/2 times p of x minus, we call it p of give me 1 second.
This is what we did last time, right?
We just said this, we didn't.
Yeah.
And in addition, for any coupling, probability that it's not equal to.
That is Q Y, right?
Sorry.
And
So
yeah,
otherwise, how do I take difference? So taking the same atom, you can looking at the probability mass for with respect to two different distributions. This together 1/2. So x. Everybody try to prove this. It's bold claim. First one is not very bold. So there exists such a coupling, but the second claim is kind of bold. that no matter how you come up with the coupling, the probability that x hat is not equal to y hat is greater than the same quantity above. So that's why this is called maximal coupling. The coupling we are going to demonstrate to get equality will be called maximal coupling. Any idea what? So I'm given x and y. I have to come up with x hat and y hat such that marginal distribution of x hat is same as x, marginal distribution of y hat is same as y, and it has this property. So any clue what will it look like? See, coupling really means is I'm trying to couple x and y. It's a very natural meaning. X and y could be arbitrary, but x hat and y hat some relationship which is displayed by this relation. So let's see one example. So suppose my coupling, so example. So for defining coupling, I just have to give a joint distribution of x hat and y hat. So probability x hat equal to y hat. Little x. I'm going to define as minimum px px. This is my symbol for the. So now I'm defining a joint distribution for x hat and y. So they're equal to some x with this much probability. Otherwise, probability that x hat takes value x, y hat takes value y is p of x minus that's my complete joint distribution. Okay, so is this first of all a valid coupling? What do I need to check if it's a valid coupling or not?
The cumulative
Can you say precisely?
fx and sy.
So x hat should be the same distribution as x, and y hat should have the same distribution as y. Is that correct here? Do I need to pass this, or this is obvious, right? What I'm doing? I'm just putting minimum of the two markers on the equal probability. And for arbitrary x and y, this quantity is p of x minus this minimum, this q of y minus minimum, and divided by this normalization. Give this normalization over anything that is essentially representative. What is the interesting thing? Because before we do anything, we should at least satisfy ourselves that this is a valid coupling. So any idea how to show that? This is an interesting quantity. Think of this quantity, sum over all x. P of x minus some lower. Does it have any relationship between the denominator? This same thing. Okay, how do you see this? Yes. So the guess is that that sum is nothing but a denominator. And suppose that was true. Can you show that this is a valid coupling? See, what do we need to do? We just need to sum this over all y's to get a distribution of x, and similarly sum it over all x to get a distribution of y. So suppose this quantity is equal to 1/2 times p squared minus q. We put a question mark on the moment. Let's suppose this is true. Does it imply that the distribution of x hat is same as x?
So there is sum over
If I sum all x, this over x, this guy is going to cancel. Only what will remain? Qy minus this quantity. And that's the only atom missing. So I will get
I think I think this is basically the when you are summing over x, you are basically getting a marginal distribution for y.
Correct.
With just excluding one term.
Correct. This q of y minus this.
Yeah,
And that is exactly
for when it's becoming.
and you do the opposite, you get x.
Yeah.
So as long as this is true, it's easy to see that it is a valid coupling.
Yeah.
But now how do you show this? That's the only tricky part. There's some just nice symmetry sitting there essentially. So it's easier to think of this equal to this rather than this equal to that. That much I get it. So if you open this up, it's easier to show that that is equal to this. Because of the mod. So where does the mod become without the mod? So only when one term is greater than the other.
Greater than the other.
Essentially, if I open this up over the sets over which pz is greater than qz, and when qz is greater than pz, something is going to happen in anybody's spot.
So I think we will have two cases, right? Because when pz will be greater than qz and
no, but this is a summation over all z. So certain terms are positive, certain terms are negative. So if I can just swap the sign.
yeah.
But then somehow that appears. Why? Give you a few moments to think about it. I don't want to rush it. It's something interesting. There's a nice pictorial way of also seeing it. You can even draw a picture and convince yourself of it. That won't be approved, but let's do an example if you're not convinced. So let's take let's say 2-point masses. X is such that it takes 1/4 and 3/4, whatever that is, and 3 matter because number don't matter. Y takes 3/4. What is the right hand side and what is the left hand side? The summation P of x is always equal to 1, so that much you don't have. So all you have to sum is the min of the two. Min of the two is always 1/4. So what is the sum on the left hand side? It's just 1/2. What is the sum on the right hand side? What's the magic?
So what I can think of is that the right hand side term, the if we only consider pz minus qz, then the total value, the sum of total positive values that we will be getting will be same as the total negative value, sum of the total negative values as well there. So
Is that true?
it feels like that, like means
No,
the
sir.
deviation
See, the
from.
way I have made it, it is similar, but I have not done some weird things with this. Right? It's
Yeah.
just 2 point mass, it appears that way.
I mean, it's very symmetric, the example too.
Because I could do all sorts
Yeah.
of things. That in that case, this is not good. Only the summation this appears to be. So it's not that I can actually break it into 2 parts. Say one part is this and one part is that. That may not be true. You can easily convince yourself that if I have a 3 point mass, I could say one by 4, another 1/4, another half, and I could do something crazy here. Yeah. So let's try to open this. What is the summation mod pz minus qz level? I'm going to write two sets that belongs to A. Then I'm dropping one. Is that okay? We raise the set there. Pz is greater than qz, or at least as Now can you proceed? Still.
So for all x in A complement, the left hand side term will be 0.
Why?
The minimum value of Px.
No, we're not yet gone there. We want to show that as a summation, this is equal to the same thing. Okay. You want to term by term, that's not true.
So those two summations are equal, no?
Which one? These two.
No, yeah.
Why? Because A could be very small set. The
Yeah.
complement would be very large set.
No, my intuition is like, so in the first thing, P is leading Q, right?
Yeah.
So Q will ask to make up
So
for it.
somewhere it has to make up because the addition of the two is equal to 1. That much is true, but there could be all sorts of unbalanced things. I could interlace, like for every atomic value, they could keep switching signs. I could do all sorts of things. What?
So we can write Q set there as Px intersection Q, whatever that sign is.
What do you want to do? We just scroll. Okay. So what do you want to do? You want to take negative terms separately?
No. So the negative, so that summation x a complement negative is that is basically 1 minus the positive part, or something like that. Okay, so it's kind of
Yeah. What you really should think about it, how do I introduce this here? The mean of the two. Suppose I would separate it. X belongs to A, positive values, P Z. Should objective.
Yeah, just good. You see.
Just take the positive values first. And the two negative values. Q minus X belongs to A. Can you write this something as a union over A union A complement?
Meaning of P X and Q X.
So that's really the only observation one has to make. This is nothing but really this. See, I'm counting over A and A complement separately. So if I were to try it as a union over A union A complement, what would I write? If I want to write the single sum, what would that equal to be? If I just want to write a single sum for both the negative quantities, what will that equal to?
Like max. It's like a max operation. Something.
Why is it a max? There is a negative also.
So no, sorry. In X equal to P of X is bigger. So main, sorry, not max.
Everybody should be convinced.
Yes.
That I can actually write this as minus X not P. This is easy to convince yourself. Even if you don't see it right now, you can just say for each X, you just brute force go from left to right or right to left. There's nothing to be done there. What do I do with the down here and down here? Can I write it as 1 minus something? 1 minus something here?
Yeah,
What can I do there?
I think for X belonging to A union A complement is, and you are coming over Px in that form, right?
Yeah.
So,
So how much is this sum equal to 1 minus something? What is that sum?
A complement Px, right? Sum of
Okay.
and then you can just take the sum of those.
That's correct. So both of them, if I write, what will I get? I get 1 minus summation of Px over a complement plus 1 minus summation of Qx over A. And minus of this quantity. Am I done? I want to do that. I'm going to move all of this up to the left. You think that is possible? Let's see. Very good. So suppose that I get this that. One minus two x x in that's one. Minus x. Okay. I claim I'm done. Don't lose sight of what I wanted. This is what I want.
Yeah.
2 minus 2 times mean of Px.
Sorry, 2 minus
2 times meaning of P and Q.
You have written that earlier. You get this term.
Just look at what we did.
Yeah, yeah.
From here we came again. Exactly written the same term. So nothing but 2 minus 2 times this. So when did I start? This whole in 2 times. Okay? So if I take 1 by 2 of that, getting 1 minus quantity. This is nothing but 1.
Yeah, I didn't get it.
Which one? This one.
Yes.
Are you convinced that this minus, so 2 minuses give you this?
Yes.
So written exactly that again, one more time.
Okay.
I return 1 minus this quantity
Hmm.
and another 1 minus this quantity. That is exactly the same quantity as we argued to be min.
Okay.
So you get 2 mins and you get a 2 plus.
Okay.
So you get 2 minus 2 times this. I move the 2 back over there. That is the quantity here. That is equal to 1 minus this sum. This is 1 identically 1. Summation of px over all x is just 1
Yes.
by definition.
Okay. Yes.
So this is a little bit of triggering, and the book somehow suddenly forgets to write the book. So if you follow in the book, you have to do a little bit of triggering in the book. You can come up with your own pictorial argument. Actually, very nice. It's a very basic standard result in computing. All right, tell me. So that's the first step here. Overcome that this is in fact correct, and because of that, this is a valid coupling. Now the job is to actually compute the probability of x hat being not equal to y hat. So does anybody get an idea what is this maximum coupling? What is so special about this? Something is going on. Anyone wants to make any comment on what is exactly going on? Again, think of this probability mass if you really want to look at it. What am I doing? I'm making x hat equal to y hat equal to little x with probability. So what will that be? It's always 1/2. The probability that both of them match. So what are you doing? You're drawing a random variable with this distribution. Similarly, you're drawing a random variable distribution x hat and y hat. I'm making sure that knowing the value of x hat, what is the probability that y hat also takes the same value is 1/4. That's what I'm essentially making sure by picking this min guys. X and y could be independent, I don't care. I'm making sure that x hat and y hat are correlated in such a way that if I know the value of x hat to be something, I know with probability 1/4, y hat is also going to take the same value. That's what I'm forcing it to do. Can you come up with any other coupling? There's no uniqueness of coupling. Can be so many other couplings. So let's just get our hands dirty. So suppose this is your x and y. What other coupling can you come on? Other than x equal to y. Sorry, x hat equal to x and y hat equal to y. All you have to satisfy is x hat has the same distribution as x, y hat has the same distribution as y. That should be too hard. Some distribution for which x hat and x are the same distribution. So try to think of enforcing an extra condition. The probability that x hat equal to y hat equal to 1. Does it simplify your task? or the complement, probability that x hat equal to y hat equal to 0. Is it possible to do so? So I'm asking either you create x hat and y hat such that is it 0. This is doing one particular. I'm asking you to go to the other extreme. Is it possible to do so? The bunch of equations you have to satisfy. Question is, does there exist a solution?
Equal to 0, probability x is equal to y.
Which one do you want?
Probability x is equal to y. 0.
Okay, so what is it? If I want to give a joint distribution, I could essentially give a 4 tuple in some sense. So this is going to take 0, 1 without loss. What is my condition? That probability of the distribution. That's next. These are the only conditions. So which way sums have to match somehow? So let this is x, okay? This is my x axis. This is my y. What entries can I put so that I make sure that this is true? So let's call them A, B, C, and D. Right? I just want to fill up this 2 by 2 matrix. And I'm given x is 1/4, 3/4, and y is 3/4, 0. Let them be in. I don't care. Because to begin with, I don't really need to know how x and y is. The joint distribution is not important. Okay, so what are the conditions in ABCD that I need to reverse? So that
A plus B is 1/4.
A plus B.
C plus C is 3/2. So we have 4.
Simple D.
A plus C is 3/2. B plus D is 1.
What about that condition of term?
A is 0, D is 0.
Okay. So what is the solution for not really B and B's?
B is 1/4, C is 3/2.
Everybody agrees to the solution? I think so. I was not planning to actually cover this. It's very instructive. So what is the answer we got? E equal to
1/4.
C equal to 3 All right. Is this a valid coupling?
Yeah, satisfies.
Yes. The most important, I don't really care about this. I don't care about this. As long as you satisfy this, it's a valid coupling. This just made my job easier. Because I made sure that I force one corner. That I'm holding one corner and I'm letting my space only go along that. That's what is happening because of probability. Otherwise, I don't there's so many solutions possible of all this. Just because you force that they never be equal to each other, suddenly you pop out these two ways. So now they're super correlated. What does it really mean? That 0, 1 has probability 1/4 and 1 has probability 3/4. Rest of them never occur. So now people have feeling for what a coupling really is. All we are doing is nothing but defining a joint distribution where the marginals match. What we are really interested in, what is the probability that x hat is not equal to y hat. So for all such couplings, what this theorem is telling you is that there is no way you can make it smaller than this quantity. Now, hopefully, one understands what this theorem really means. In that example, there's so many possibilities, right, for couplings. You could choose A, B, C, D as whatever you want. What this theorem is telling you that no matter how you choose it, you cannot go below. And this quantity is fixed. As far as x and y is fixed, this is fixed. This is not a variable you can choose. This is the universal constant. As soon as I specify x and y, this is fixed. For all possible couplings, showing them the probability that they don't match is at least so much. If you had tried starting saying this is 0, something would have gone wrong. That's essentially what it's telling. So suppose you started looking forward for my example x and y. Let's fix the probability that x hat is not equal to y hat is 0. What is telling you that you can't find one such coupling. I'm just flipping it up. We say if the coupling exists, this is true. If this is not true, there can't be a coupling. So the example we took, we tried to make sure that x hat equal to y hat was 0. If you had insisted x hat not equal to y hat is 0, that those set of equations possibly not have a solution. Okay, so far so good. Now how do we really prove? So we wanted to prove that last. Now, people remember my construction. The construction is this is my maximum coupling. So for this coupling, I'll show the bound, and for every other coupling, I'll show that this is lower bounded by this. That's what my goal is.
Just on the result, like what is the interpretation of that? What is the significance?
So, as we just said, like, suppose if you insisted that this probability is 0, you will not be able to find it. See, how do I answer such questions? You come up with tomorrow, point one चाहिए. I want points. I'll say that because you're also specifying x and y ahead of time, and that controls this quantity. It could be that if x is equal to y, this quantity is actually identically 0. Then you can do whatever you want. So, given the starting point of x comma y, this quantity is fixed, and as a function of that, you're able to tell me does there exist a coupling with such a property or not. So both ways, you can go both ways. So this is what I want to prove. So first we show that in fact for the choice I given you in the next slide, this is equal, and for everything else it is greater. So just to recap, this is my maximal coupling. They're equal with the minimum of the two probabilities. They're taking arbitrary values x and y. These are nice symmetric terms. So hopefully you see which number you want. And this is just normalization. You can actually copy it. Oh, so we have x hat not equal to x be equal to x y. Here x minus they're just summing over all the terms which are not in the first one. The only thing which you have controlled, okay, there's something. Try to do math on it.
We can press undo.
No, it will undo the final thing.
Oh,
So if you are little in your notes, the only term I'm not adding is the first term where x hat was equal to y hat equal to little x was we know p of x comma. Everything else I'm just going to. What is this?
Second term should be, one should be y, q, y.
They keep me honest. These kind of mistakes can happen. Okay, so what is this? You just trigger some.
Yeah.
so if you sum it on one variable, then it will cancel.
Yeah.
You can see if free is one, you add this thing, which is proven that this tree is nothing. All you have to get is summation of this, which is exactly equal to this. So you end up getting. That's what we wanted. First claim we wanted to make was there exists a coupling for which this is true. And for the candidate, we got this. Now we want to show that for every other coupling, this is at least abnormals. Okay, so now any ideas I can do that.
Yeah, I didn't understand one thing. I mean, why are you summing it?
So what is the problem? See, this is if I expand it, this can you tell me what is this? That x equal to x, y equal to 1. Such that little x, little y. Isn't that this is not?
Yeah.
So that is erased, but if you look at your notes, this is exactly what we see. When I'm writing random variable is not equal to random variable. This is exactly what it means. Over all possible combinations where this takes value x, this takes value y, but they are not equal. That's precisely what this probability is. That x hat is not equal to y.
Yeah.
It's just a long form derivation. We're tossing two coins. What is the probability that they don't match? That's all I'm saying. So they're all possibilities, right? Tails, heads, as well as heads, tails. So I'm just adding one else. Okay, so now how do we show that for no other coupling, we can go lower than this? It's not too hard. If you look at our example, something you can do. There are certain constraints on the fact that x hat has to have the same distribution as x. It is the only constraint given to me. X hat has to have the same distribution as x, y hat has to have the same distribution as y. Everything else is okay. Why does that enforce that this is at least so much? And again, it will come down to showing that 1 minus this summation is equal to this. So somehow you have to connect those constraints given by the coupling to 1 minus summation. Now that is related to this quantity. And that we know is nothing but the denominator. That's what will give us our third. What is the constraint? That x hat and x are the same distribution, and y hat and y hat the same distribution. So you can just put a question mark first and then we'll take off. Is it so? Yeah. Just by condition. Because the probability that two events happen simultaneously is better be smaller probability than one event. Now this is by definition. requirement that they better have the same distribution. And this is by definition. So this is true always. This is event even intersection E. Why this is just E. So that better be this. And this is both are by definition. This is a requirement, this is a definition. Similarly, what I can do? I can get some Q of X similarly. Just shifting the roles. Like y hat equal to x here, y equal to x. That means fine. What more do I have? Do I have any other leverage? What are shown? What are these two events?
The same.
Equal.
Yeah.
But I'm showing that they're less than equal to P of X as well as Q of X. So they better be less than equal to min of P of X comma Q. Now you see why the min is naturally appearing. This implies okay. Now what is the punchline?
Can reverse it. 1 minus. Also, Stochastic is summate over everything.
That's pretty much it, right? Kind of done. What did I want? I wanted x hat not equal to y hat as a random variable. So there's nothing but summation over all these complements.
Yeah.
That is nothing but 1 minus the summation of this. What do I want? I want what will be x hat not equal to which is nothing but 1 minus the summation of x. We just substitute summation here. Same as before, in the definition of x hat not equal to. And this quantity I know already proved that this is 1.
Here this is greater than equal to that.
This is greater than right. Because was less than equal to so times. All right, so anybody wants to recap what happened? So you should get a coupling feeling of coupling very well. This is going to show up everywhere. Not just for graphs, even for when you go to stochastic. Well, all sorts of couplings will happen. What you really want to do is to compare two graphs. That's really at the bottom of it. You want to say one graph is a bigger in stochasticity compared to other graphs. And the idea is to actually couple. You want me to go over it? You can go over it. Okay, so what is the coupling? Coupling is nothing but a very simple requirement that x hat better have the same distribution as x, y hat better have the same distribution as y, and both of them are defined on the same property space. So now essentially we are making them comparable by defining them to be on the same space and connected to the problem that we're generating from. It's connected to x and y respectively. And I'm free to come up with any joint distribution I like, as long as it on the columns of the rows it manages to satisfy the same constraints. Now the theorem that for any two distribution x and y, there exists a coupling such that the probability that they don't match is governed by this quantity, driven completely by the distribution of x and y. And you cannot find any other coupling for which the probability that they don't match is smaller than the same quantity. And to show you that really this example was kind of misleading. That for a two mass point system, you can actually come up with all the equations come directly from here. These many solutions exist, but if you impose an extra condition, suddenly you can actually get a simpler solution. I will just ask you to go back and play what can you do. If you look at the theorem, you try to see What if I were to look at 0? What really goes wrong? Something should go wrong. But if I insisted that my probability that x hat is not equal to y hat is 0, you should not be able to come up with a coupling. That is either x hat will not have the same distribution as x, or y hat will not have the same distribution. All right, so now let's look at an application of this theorem. Looking to ask questions, and I said earlier also, no hurry to do anything.
So we have many choices of a coupling for x and y.
Yes.
So what would a choice be like? How would we choose one?
Depends on what you like. One is essentially you want to minimize the probability that it will match. See, what are we really after? The example I gave you last time was I want to compare Bernoulli versus Poisson. I want, in some sense, a coupling or to show somehow that these two distributions are not too different. Because it's very hard to work with one distribution, while with the other it's very easy to work. So if I can couple somehow, saying if I can prove something, the probability with which that doesn't happen for this random variable is small, I'm good to go. That's what really this coupling is going to tell us. The next theorem exactly is going to lead us in that direction. So it's an application of it. I can't say that one coupling is better than the other coupling. All it is telling you is that you can control the probability of them matching or not matching. So if you're tossing two different coins, what is the probability that both of them give you the same outcome? If they're independent, you can simply compare. But you transform to some other random variable where it's very highly likely that both of them are going to give you the same answer. What system do you prefer? Well, it depends on the application.
So where does convergence frequency?
We'll get to that as well. So only as something goes large, something happens. It's not true. So what you're going to say is not going to be true for a smaller. So suppose you have just one edge graph here, another one edge graph here, things are not going to be looking very simple.
So like when we are defining coupling for only two random variables.
For the moment.
Yeah.
Because we want to consider two systems with two different random sources. If you wanted to have three systems and want to do something, you would have possibly done something more. But because this can be extended to 3, 4 as well, where you keep asking for mutually that x meets x hat in the distribution, y meets y hat in the distribution, and what z meets z hat in distribution. What is the probability that x is equal to y equal to z at the same time? You would just keep extending it. So that will extend naturally. We don't typically need it. The n large or the convergence will come before that two random processes only when, so think of large graphs. So only when the number of edges is large, we can actually approximate one binomial with a person. It's not two others. If you just a very small graph,
Sorry, I don't have any background on graph. What do you mean by graph?
you can't get it. So just think of Facebook, there is no Facebook here. So put an edge between two people who are friends on Facebook. Okay. That will give you a graph.
Yeah.
That's it. You're not going to really use any graph for this. You just take two people and put an edge between them if they're friends on Facebook. There will be a complete description of the graph. Some of them have an edge between them, some of them don't have an edge. So put all possible 6 billion, 7 billion people, keep putting an edge between them if they're friends. You can say friend also is fine, but that's also. So whatever description you want to make, that will give you a graph. And make sure that I don't use anything which is not developed in the class. Okay. So that terrible notation I always avoid. But we'll just stick with this. You see the problem. When you're writing a paper, don't use this. Capital I, subcapital I. Just impossible to read. I have tough time convincing my students not to use it. It's just bad. There's no answer. This is my notation for independent. This is standard in many problems. So whenever I'm going to talk about independent random variable, I'm just going to use this. I independent random variables. Bernoulli What that means is I equal to 1, probability PI 0. That's what it means. Right. It's B summation. Well defined random variable, nothing but binomial. So X is nothing but binomial. The other side, let's say Y is a Poisson. With parameter lambda. What that means? Probability that it is e to the minus lambda. Make sure that I write something. I'm pretty proud to making a mistake in distribution. This everything is correct. Okay, these two distributions, whatever. Then exists a coupling X hat. I'm not going to write again of X and Y. It's meaning automatically. X have defined, Y have defined, so X and Y means the respective. Such that probability that X hat not equal to Y hat is less than. Just parse it for yourself. Otherwise, I will not be able to connect anything. So PIs are the probability with which this indicator variable takes the value 1. And I'm summing n on that. That's my random variable X. The right hand side, I have a positive random variable with parameter summation of PI. Okay. What this says is that there exists a coupling X hat Y hat. That means X hat has the same distribution as X. Y hat also is Poisson distributed such that this quantity is no more than summation PI square. What is an application of this? So suppose I give you this figure. How do you use it? You know, my goal is to show that something is similar to something. So I want really this probability to be small. If I wanted to say something about one distribution, or one random variable, and I know something about that this random variable most of the time takes the same value as some other random variable. That would be a good thing to do because I can analyze one and transfer that result to the other. So ideally, I would like to have this as small as possible.
I don't follow, but continue.
So what? So suppose there is X hat, there is Y hat. Suppose I can make a statement about Y hat.
Okay.
It's a random quantity, but I can make a statement. Now, if I can control the probability that when do they don't match? So if that probability is small, whatever statement I prove for Y hat, I can transfer it to X hat with that large enough probability.
Okay.
So I would technically like this quantity to be as small as possible. So how do I make this small? Notice something strange happening. The summation is n. Then some n things will sum. But what is each term? This has suddenly become a square.
Yeah.
So if I choose pi to be how much?
Less than 1, then it will.
Not less than 1. I need to choose it as a function of n for this to be meaningful. So suppose it is 1 by n, then what happens? This probability is going down as 1 over n.
Yeah.
So as n increases, the probability that these two distributions don't meet is going to 0. Linearly. So this is how we actually need to connect it. So that's why n large. Why n large needed? Because of this. If very small, I can't do much. I need n better be large so that I can say something. So really, what is the statement you would like to make? That when Ci is some, let's say lambda by n. You fix lambda and make this lambda by n. These two graphs are going to look ways. These two random variables are actually going to look ways. Realization by realization. It's not sufficient to say the expectations are the same. There could be so many distributions which are the same expectation. Doesn't mean that on a realization you get to see the same value. Here they are being asking something very strong. On a realization basis, how often do they match? So think about the strength of the state. The fact that I'm realizing pi hat, I'm realizing x hat. How often do they match? They match with 1 minus 1 over n. That's the power. Okay, so we will.
So, the statement that you have written that this is less than or equals to pi square. I mean, how do you know that?
We'll prove, use the theorem which we prove. Okay. It's just an application of that theorem. We've done all the hard work. Now it's just a matter of showing this. Okay, so what will we do? What did our theorem tell us?
Theorem includes your other side.
We'll get it up.
Right.
Theorem was less greater than this.
Yeah, less. That is correct. So what was our maximum matching? We had a specific construction for maximum matching. That they match
Maximum
with
match.
certain, not matching. Sorry. Just to use to. Alright. Will hurt me throughout. Hope you remember. This was clear that when it is not equal to this, and it was equal with probability, we know that. So let's just try to do that. So we had I as was defined. Let Ji also with Pi. Okay. See, J was the total thing was summation of J's. Independent Poissons add up to one single Poisson. Yeah. Hopefully, all of you see that. So that much I'm going to assume. You can split a Poisson independently. You can superimpose a Poisson. It remains Poisson result. Now let's define. So rather than defining directly x hat and y hat, we're going to go by I hat and G hat. Using our maximalist expression. So what this should be really mean of the two. The mean of Pix and Qix. So this I can also write it as Pi times indicator x. What should be this really be?
Yeah, I don't understand this.
We just use it.
No.
This one.
Yeah, what
This
is
is
it?
indicator. So indicator is nothing but indicator event A is 1. If A happens. Zero. So tomorrow is going to rise. At what time? Time. So binary events. Think of it as binary and variables. It's just getting. Okay, so what will this number be? This will what is this? This is the PI.
Yeah.
So how much is it?
Yes.
Okay. A to the minus PI x x. Going.
Yeah, because x by x factor, right?
Okay, so I want to bin of the two. How much that should be? Depending on the value of the x, you get different numbers.
Yeah.
So how much is that? It's with three possibilities, but let's say x is equal to 0, what you'll get x is equal to 1. This is really deep.
Yeah, I mean,
The guy on the top cannot take value to.
yeah.
So only non-trivial things are these two.
Yeah.
So what are the possible values of the mean? No, some relationship between. Is it true? So can you choose for x equal to 0, which one of the two values will actually show up? It's really what I'm trying to do. It's taking the mean of the two values for each value of x. So what will come here and what will come?
For x equals to 0, I think 1, right?
1.
I mean,
At x equal to 0, what is the value here? X 0 minus 1.
0 vector is 1, right?
Yeah.
So basically 1.
What is this? 1 minus
1 minus 1.
Two
Oh, sorry,
minus
I think minimum. Yeah.
It's okay.
Yeah.
It's just to getting our hands dirty with it. And how much will be this? We just choose this. Is it clear what is going on?
Yeah.
That is most important. All I'm doing is I'm taking the win of the two values. So what is x equal to 1 will show you? It will be P man.
Yeah.
And for x greater than 2, it's now I want to define. So everything else is the same as our previous construction. So I'm not going to write long summations. I've given you the so I'm exactly using the same construction.
X equal to 0 and 1 be 1, right?
Okay, what is it?
I think the E it's just e to minus ph, not minus pix. This
What should I do with the x here?
X is not there.
It's not there, very. We use this. So 1 minus pi is less than equal to e to the minus 1. Okay. All right. Now can somebody finish the argument? All you need to do is to define I hat and j hat. What is the simplest way to think about it? See, you already ensured by the previous theorem that I hat matches with I hat. Sorry, I. This is the terrible thing. This is same distribution.
Yeah.
For the previous theorem itself. Right. So if I take summations of this, so this is a that if I take x hat, it will be summation of I hat. And so the same distribution x. Similarly, I can impose these AIs, which is nothing but y hat. That much is ensured. What do I need independence of i's and j's or not? I need it, right? These so I've chosen I hat and j hat using this. When I'm going from here to here, I need to make sure that these guys are independent of each other. Then only this distribution is going to match x. Okay, what if they are dependent on each other? I'm not giving you anything about the joint distribution of I1 hat and I2 hat. If I make them independent to each other, will this be true? X is independent to each other. X is just a summation of independent IIs. Okay. X by definition is a summation of independent IIs. Similarly, Y is nothing but summation of independent Poisson random variables P1, P2, P. Independent random variables. And I can essentially write this Poisson as a split of independent random variables P1, P2. So what I'm doing by construction is these guys are independent by choice. And I'm adding these medium. So coordinate wise, these guys match each other. And I take independent collection of them and add it together. X hat matches X, Y hat matches Y. Alright. Now what is it? So what was our probability? What did this theorem actually tell us? It told us something. Where probability I hat not equal to J I hat. For how much? Greater than this is okay. But if you were to just somehow bound this, let's say, using this, what will that bound look like? This is 1 minus the probability that I have equal to J. And how much is this quantity?
1 minus sum of the right?
Yeah, it's not right. 1 minus pi
Minus ci.
correct. Is upper bound is completely.
It's a negative quantity, right?
Again, we use the same.
Pi
times 1 minus
It's not a negative.
it's not negative quantity. Yeah. Pi times 1 minus.
Yeah. So this is pi minus 1 minus e to the minus.
Yes,
So component wise, I'm able to upper bounds.
I think so that's equal sign, right?
This one?
No, equal that.
This one? Yes. That is good. But is the equal to this one? True equality. Basically right. Okay, if you insist. Oh, now what do I do? Give me the punchline.
Any union one. X is not equal to I hat, and one of them is not equal.
Right. So what did I really care about? I've done this component wise. What I really care about is probably the x hat is not equal to y hat. How much larger can that really be? So what do I want? I want probability that x hat is not equal to y hat.
I think those are independent, right? So you can just take the sum directly.
It's not going to help. Okay. Because it's summation of independent ones are not going to somehow split. Yeah. So you have to resort to sum. So it's So, simple, make as the pretty medium.
Plus, it's exactly plus 5 is plus that.
Why did it go?
Extent is not equal to as and has to.
Union.
So when the union comes out as a summation, you can put less than.
Okay.
When it's inside 5.
Okay, let's not, so it could be, I don't think it's true, but I don't have a full answer why it is not equal. I don't think it equals. It could be some pathological case where, but this is always less than equal to zero. That suffices for our part. But I might have to think a little bit why it is not. This is equal to. Probability. So we didn't use, so what did we use from the theorem? We used the construction to show that it's a valid coupling. We didn't actually use the bound which came from there. Because as you said, I want to reverse direction. So the bound there you would have got would have been a different direction altogether. Now you can go and check that does it match this. That would be an interesting exercise. Because we use the same construction.
No, I'm trying to understand the second.
This one is also called Boole's inequality. If you want to do it yourself, need that.
X hat is summation in I hat, right?
X hat that we have defined. X hat is summation of I hat. Y hat is summation. And they are independent.
So we want X hat not equal to Y hat.
Yeah.
What is that union I hat is not equal to G I hat.
So what is the event probability of A union B? But
Suppose I one hat is not equal to G one hat, and also so it could happen that none of the I hat is equal to G I hat, but their summation could be equal, still be equal, right?
that's what you have to prove. That's what is it's a non-trivial fact.
Oh, but the lesser equal to is fine. Lesser equal. So
Now, what are you saying that so it could be that X hat is equal
that's
to
why
Y
there's no
hat.
equality. That's why we said less than equal. Because those cases could have a bigger set. Because it can lead to equality also, but
No,
No, but left implies like
so left implies right, then it's correct.
Hmm.
Then less than equal to is correct. If A implies B, then P of A is less than P of B. Which direction are you saying?
so it could the right hand side could happen, but it could happen that X hat is equal to Y hat.
No. This is A. And this is B. What are you saying? B can imply a complement.
Yes. Yes.
Okay, then what would happen? A will possibly imply B complement.
but also
But
A
we
implies,
don't care much for this.
but A implies B, that is true, right?
That's all, but even if this was true, I don't get a refutation,
Yeah.
refutation of this. Okay. You can prove it yourself, or you can just look up. It's called Boole's inequality. So eventually, what you end up getting is that there exists a coupling, which is the maximum coupling, such that the probability that those two random variables don't match. So the most important thing is this square term. If it was just pi times summation of n, it would be useless. All you will get is a constant. So it's very important that the quadratic term should be there. All right, any questions? I'm going to introduce another concept for stochastic ordering. It is highly related for this you might have seen. Maybe is more ignorant. So let X and Y be not necessarily in the same space. Then X this way, here this way. Yes. Y. It's here. For all X. Also represented that X. Any example comes to mind quickly? We all know two deterministic things I can always compare. Here I'm trying to compare two stochastic things. So there is a domination from the cumulative CDF essentially. This CDF always remains below this CDF. There is no point where one can go down. What's a simple example?
We can take the same two distributions and shift one. So,
That's too trivial. So keep working. I'll just write a statement. That'll prove next time. But keep working on the exam. Don't look at that. Just keep working on the example for stochastic inconsistencies. Just one non-trivial example. Like for example, two different units. Very good, but show me without knowing the distribution also. I'm okay with that, but you're not allowed to use the formula. Because otherwise I ask you why is the e to the minus something really written. You have to convince me. So to do that, this formulation actually comes very handy. What is saying is that X is stochastically dominated by, but only if there exists a coupling X hat Y hat, such that the probability that X hat is less than equal to Y1. So now you're allowed to use this to construct your example and convince that some distribution is stochastically dominated by the distribution. If you want, don't want it, fine. This statement makes sense?
So in that, so the X hat less than equal to is stochastic ordering thing they put here.
No, this is clear.
Normal.
This is just what is the distance? This is just the probability mass of all points where X is less than pi. That's there is a big, there exists. Don't say for every possible coupling this is not. There exists at least one such coupling for which this is. So this may not be true for X equal to X hat and Y equal to Y hat. So don't try for every possible coupling. So how would this example work? Remember the definition of I go from 1 to n and I. Take this as X, then Y. You to convince me that one is stochastically ordered compared to that. Just obvious which one is. But can you convince me? So it's a weird distribution to come up. It's clear, right, that y is weaker than x. I'm tossing the coin n times, I'm tossing the coin n by 2 times. So it's most likely that the distribution of x is a little opposite. So to speak. But how do you convince me that? Leave the complete if you want. Just use that. Take x equal to x hat, y equal to y hat. What happens? What is this probability if I take x equal to x hat and y equal to y hat? So these things. The reverse direction is change. What is this probability? Why is it not one?
It could be, it could be zero, and y could be positive.
So that's the trick in how we define x hat and y hat. How to define? I am allowed to take any x hat and y hat for which the distributions are the same. So I make sure that whenever pi is 1 for this, is pi is also 1 for that. And that's a valid distribution. How many of them are there? N. 1, 2. So let's say this is n. This is n by 2. What is going on? Some indicator. Let's say this is 1, this is 1, this is 1, and then this is 1. So why can't I make x summation of all these ones and y summations of only these many ones? This will match the distribution of x and y. So what are you doing? You're generating n such indicators. Take the summation of the first n by 2, call it x hat. Sorry, call it x. Sorry, y hat. Okay. And take the same summation of a superset, call it x hat. X hat will match with the distribution of x. Clearly, they're not independent now anymore. That's the only difference. So your problem was they appear to be independent, but they're not independent anymore. So the same process is giving rise to. Is clear what I'm doing? Think of forget about x and y's. Some process is generating these ones. Whichever ones I get to see in the first n by 2 places, I add and call it y hat. And whichever ones I get to see, which will contain all the ones I've already counted, as x hat. Now x hat is going to have the same distribution as x. Y hat is going to have the same distribution as y. But definitely this is equal. For that choice is x. What this theorem tells me that if such a thing exists, definitely exists. So it's a great application of the very simple theorem. Otherwise, it's a nasty business. You can show it in many different ways by just directly computing the distribution. This is a very clean way. So it also tells you how to couple things so that you can get something. Okay, so let's
We don't
start.
need n by 2, right? It could be n by 2.
Anything which is smaller than n. It will work. Alright, so let's stop here. Let me